Sorry for the delay. Good morning, everyone. My name is Chen Mao. I'm a graduate student from the Department of Construction Management in Tsinghua University. Today, my research topic is about assessing the impact of interdependencies on the resilience of networked critical infrastructure. So firstly, critical infrastructure systems are defined as networks of man-made systems and processes that function capability to produce and distribute goods and services, such as electric power systems, water supply systems, telecommunications, transport systems. And in reality, various components of CIS are highly interconnected and interdependent. This interdependency is defined as a relationship between two CIAs, which means the state of one CIA can influence the state of the other one. These interdependencies bring not only efficiency but also risks. Here are the process of city respond to hazard events. Interdependencies can aggravate the disturbance propagations and also can decelerate the system recovery. For example, in 2008 Chinese winter storm, the failure of electrical power facilities led to the breakdown of communication and heating systems. And the failure of transportation facilities led to more difficulty in the emergency restorations and also the force inaccessible to power plants, which resulted in the electrical power shortage. So it's urgent to measure the city performance level during the whole process, since the concept of resilience was proposed. Resilience can generally be divided into two parts: inherent and adaptive. Inherent means making the system less vulnerable in the resistance stage, and the adaptive means taking extra effort to make the system recovery more efficient and faster. This concept of resilience provides a new perspective to assess the, both vulnerability and recovery. So my research objective is to assess the impact of interdependencies on the overall level of resilience. To be specifically, it can be divided into two parts. One is the impact of system performance losses, and the second is the impact on system performance recovery in the restoration stage. So we adopt simulation-based methods by using various existed and typical models. And 10 simulation settings were conducted with different modeling approaches and resilience matrix. One setting means a group of one modeling approach and one resilience matrix. The purpose of these simulation settings was to ensure that simulation results were independent of modeling approaches and matrices. And we adopted a hurricane model to simulate the hazard events. Parameters including altitude, land use, and structural strength were used to determine the probability curve of CIS. And 12-grade typhoon was selected in the case study based on the historical hazard analysis. And the simulation of this hurricane model, the simulation result of this hurricane model is the failure probability of each facility. So in this case study, it was assumed that CIS facilities whose probability of failure exceeded 50% were regarded as failed. And then we adopt 4 typical network-based models to simulate the interdependencies. Whereas nodes can represent built facilities, links represent relation connections. So in the first simple network model, when there is a connection from node A to node B, so if A fails and then B fails. In the second probability model, if A fails, the node B doesn't always fail. It has the possibility to fail. And in the flow model, each node and or link has 2 properties. One is the flow, the second one is the capacity. Flow means the current amount of goods the link or node delivers, and the capacity means the maximum potential flow. So the flow cannot exceed the capacity. So if ABC, node ABC in the same CIS and A fails, so the flow of node A will decrease linearly. But if B in a different CIS from node A and C, the capacity of node B will decrease. In the nonlinear flow mode, if the flow of A decreases to a certain extent, it will satisfy the demand of node B firstly. So which means the capacity B will keep on a certain extent, such as 50% in the case study. So in the restoration simulations, we made several assumptions. First is the only nodes failed directly due to hazards need to be restored. And the restoration efforts were undertaken separately in each CIS. One node could be only one node could be under restoration at any given point of time. And the sequence was determined based on population affected by nodes, and the performance curve of a failed node during the restoration stage was set as this formula. It's based on the work of this last one leader. And we finally adopt 3 resilience metrics to assess the resilience. First one is the critical path length, which means the average of shortest path length from all 2 nodes. And flow transferred means the current flow transferred in the CIS. And the population satisfied means how many people or how many people's amount was satisfied in the current time. So we took a middle city in southern China as a case study, and the CIS including electric power systems, water supply systems, and telecommunication system. And here are the main facilities and the number of them. And as below is a network of each separate CIS and the network of interdependence between these CIS. So in order to assess the impact of interdependencies on the resilience level, so we set 3 simulation scenarios. specifically by whether considering interdependencies in the resistance or restoration stages. And considering interdependency in the resistance stage means the disturbance can progress through interdependencies. Not considering means each CIS is separated. There is no disturbance progression through these CIS. And consideration interdependency in the restoration stage means we have to optimize the restoration sequences by calculating the population affected in all CIS. So here are the simulation results. It's the resistance stages comparing simulation scenario 1 and 2. And we can find that interdependencies aggravate the disturbance progression and lead to more system performance losses in all 10 simulation settings. And it's the restoration stage comparing simulation scenario 2 and 3. You can find the recovery and the resilience is improved when the restoration sequence is optimized by taking interdependency into consideration, also in all 10 simulation settings. And here's a specific resilience assessment in different simulation scenarios and settings. You can find comparing simulation scenarios, scenario 1 and 2, and there is a distinct decrease of resilience. And comparing simulation scenario 2 and 3, there is a distinct improvement of resilience. So as conclusions, this study we simulated both resistance and the restoration stages of CIS response to a certain hazard event using 4 network-based models and assessed the resilience of CIS using 3 matrices. And the results in all these 10 simulation sets showed that the interdependencies had a significant impact on the performance and resilience of CIS. And this approach described in the study is much applicable to CIS which are well networked and whose faults can be measured and recorded. And as a future work, we are going to propose resilience investment optimization framework based on the simulation process presented in this. Thank you. That's all my presentation.